Okay, should be up now. Okay. Hmm. Let me just bring the notepad. Hmm. So I'm hoping somebody did try this question as I had asked you to. And okay, it was here the whole time. Hmm. Okay. Here we go. All right. So, okay, the question is, given that you have a binary tree, it's not binary search tree or anything. So given that you have a binary tree, your objective is to uh, connect all the nodes on the same height with the next pointer. So let's see how our flow would be, right? So let's assume this tree, only the one given in the example. So what you want to do is, so okay, so the rightmost node will always point to null, right? So you don't care about the rightmost node as such. What you really care about is all the nodes on a level. So on the first level, you will be processing only one, and you see that okay, there is no node to be processed after one, so one points to null. Then you want to process 2 and 3, which are the children of 1. So when you process 2 and you want to process these as a part of a set. So when you want to process these, you see, okay, so you have 2 and do you have any other items in the set? Yeah, next is 3. So you make 2 point to 3. Then you process 3. And you see, are there any items right of 3? No, then you point 3 to null. Similarly, now you want to process the children of 2 and 3. So you have to process 4, 5, 6, and in this order. So you see, okay, 4 has so say we get the set 4, 5, 6, 7. So if you want to process 4, so is there anything to the right of 4? Yeah, so 4 next is 5. Is there anything next to 5 to the right of 5? Yes, you have 6. So 5 next points to 6. Similarly for 6, 7, and for 7 there's nothing to the right, so you point at null. So this is looking at the straight up obvious case where each node has two children. So let's say one of them doesn't, in the middle somewhere. No problem. Since what we are considering is not some children or some, uh, you know, some order of children where we processing the left first or the right first. We what we care about is our sequence currently. So this right now for us, we have four pointers, three pointers, one pointing to 4, one pointing to 5, and one pointing to 7. So that's all we have. So we don't care whether 7 is the right child of the parent or the left child. So when you process 5, you see, okay, does the sequence have any other nodes? Yes. Then 5 dot next becomes 7 and 7 dot next becomes null. Similarly, if we didn't have 4, no problem. We would have the sequence would have started with 5 and we would have processed that accordingly. Even if say 2 didn't have 5 and 3 had two children, again we would be looking at only our sequence and not care about anything else. So if you can recall how we create a sequence of all the nodes at a level, that is BFS. So basically you process one, then you push all its children, then you process everything you're having the list right now in the queue 2 3, and you process them and you push their children in the list. So every time the sequence contains all the elements that are in at the same level, no matter if they're if you talk about distance, maybe as if you're skipping nodes at that level, even if they're distance 1 2 or whatever, even if these nodes have children, how many ever, they're going to be processed next. So you'll be processing each level in the queue one by one, and that way, while processing the level, you check if your queue is not empty, then you make the make your current processing node point to the top of the queue. Else, you point it at null, which will be the last step anyway when you're processing the last node in the queue. Simple as that. So yeah, I did figure this question out myself without looking at the solution uh, while working on trees on IB. So I think it's populate next right pointer tree. Yeah. So let's just do this and return A. Sorry, return root. Oh, yeah, I knew that if root is null, return. Oops, sorry, I'm hiding the code right now. Hmm. Here's the code. So simple BFS. You have a queue and you check if for all the elements in the queue, if I is not zero, basically. I guess this is taking care of just the first. Hmm, uh, when there's only one element. Yeah, you don't even need to do this. I mostly did it when I was not very experienced. So yeah, it just has to be simple BFS with the logic that I had explained earlier. So I'm going to submit this now and it is going to work perfectly fine. Awesome. Oh, there's a number two to it. Okay, cool. All right, so we were at next point is best time to buy and sell stocks. Oh, I think we've done this already. Yeah, so the question is, say you have an array where you've given the prices. You can do at most one transaction a day. I mean, like you have to, not a day, but you have to sell a stock before you can buy it again. So basically, if you're at 7, you buy at 7. You have to buy at 1, you have to first sell at 1 or sell at 7, which should not make any sense, but yeah. So this one has a very mathematical kind of logical answer where I don't know if you will be able to, if you'll be able to see it, then it's sort of obvious that you always buy at a lower price and then you sell at a higher price. If ever in between you skip the same, which means you would be missing an opportunity to make a profit. So, so yeah, just sell on a profit. And if you're gonna be making more profit some other day, then just sell what you bought before. So basically, you buy every day. Yeah. Given that given that the next day you can sell it. That's all. So say you buy at 7. If you can sell it the next day, only then will you buy at 7. Otherwise, you drop this. So you go to the next place, you buy at 1. If you can sell at 3, just if you can sell it the next day, just sell it. So if you think, oh, it's better if I sell at 5, I'll make a profit of 4. So if I skip 3, so it's not gonna matter because if you buy at 1 and sell at 3, you'll be making a profit of 2. Then this is gonna come up for sure, right? This combination. So then you buy at 3, since this holds true for a condition that di is greater than di minus 1. So buy. Uh, so you buy at 3 and sell at 5. So you make another profit of 2, which makes your total profit 4. So it doesn't matter if you, so you don't have to check, oh, when should I sell? Oh my God. It's not the best time to sell right now. So you don't need to worry about that. If you're making a profit, just sell. And if you see in this case, so say if you'd gone like in this direction, you would have made a total profit of 3. And if you buy here and sell here, you would make a loss of 1 from this 4 that we just did and made 3. So you don't do that. You just don't do this. You buy here, buy here, sell here, and then don't do anything with this combination. Just move ahead. You'd say, oh, if I buy at 5 and then sell at 10, I'll be making a profit of 5. Well, if you don't do anything at 5 and you go to 4 and then you buy at 4 and then sell at 10, you'll make a profit of 6. So always buying at a lower price makes sense, right? So if the next upcoming price is lower, then you don't buy right now. You buy lower when it's later when it's lower. And if the price is higher, then you buy today because tomorrow you can sell it. Yeah, simple as that. And same things in the code. Oops. Yeah, might have done it in a weird way since again, it's like I'm writing code for the first time. But essentially, you don't need to erase or do anything. Just iterate over the array, and if the current price, hmm, just forget this code. If the current price is less than the next price, then just do the trade. Buy it today and sell it tomorrow. Just that is the profit you'll be making. So just calculate that profit and move on to the next day. Because the next day you'll be looking at buying only, not selling. So you don't have to do two logics. It's just one logic of buying and selling of for current and next date. Okay. Um. Cool. So if you see, from this list, we've already covered almost half the questions, I would say. Um, which should lead you to believe that we are on a good track. It's not even been a week since we started lead code. Not even a week. And you're halfway through, almost halfway through clearing an interview if you've been following since the start. So that's that's great. Um, okay. Okay. Next question is word ladder 2. So we've only done questions till 1 to 1. Um, I think we were at like 130 or something. No, we're not done this yet. We're only at 113. This I did randomly, not in order. So yeah, so we aren't actually um, yeah, we haven't done any of these questions. Okay. So I think it might be better. Okay, anyway, since when I'm solving these problems, I am solving them with you guys itself, so might as well solve these problems with you. I'm not sure if it's a great insight or not, but let's see how that works out. So given two words and a dictionary's and a dictionary's word list, find all the shortest transformation sequences from begin to end such that only one letter can be changed at a time. Each transformed word must exist in the word list. Note that begin word is not a transformed word. Note. Return an empty list if there's no such sequence. All words must have the same length. All words contain only lowercase alphabetic characters. You may assume no duplicates. You may assume these are non-empty and not the same. So basically, Given hit, COG, and a word list. They're both length, right? They both are the same length. All words are the same length, yeah. And given a list, find all the words that would come between hit and COG. By only transforming one character in the word. Hmm. Okay. Okay, so in case you didn't understand the question says, say you're given two words. One is, say, is the stream okay? No. Oh, sorry, again. Screw up. Yeah. Yeah, so the question says if you've given two words, say one is hit and the other one is COG, and you're given a list of words, hot, dog, log, etc. And you have to figure out uh, all the all the sequences that you can apply on your uh, source, let's call this source, to convert it into your destination, such that at every single step you are changing only one character from the word at max, and also that change is only allowed if after doing that change the answer lies in your list. How that makes sense? Okay, so let's think about. So obviously each word is going to be used at best once, and the number of words in your sequence is going to be dependent on your source. So basically, if you have H, I, T, and say it is COG, so based on how many characters you have to change, so say we have to change three characters, right? So it will take at least three words in between hit and cog to have a final answer. So it will be like hit, hot, sorry, hot, um, hog, dog, cog. So we change the middle one, then we change the last one, then we change the hot, hog, then we change the first one, and then we change the first one again. So yeah, we could have gone directly from here to here. So sequence size is length plus one. I'm just stating facts. This information may or may not help us. Hmm. Now, one thing we can do is maybe calculate the distance between all the words. And by distance, I mean how many characters does it take to change? I mean, not just actually calculate the distance, but check how many of the words are one change apart. So hit can be converted to hot in one change, and similarly, hot can be converted to dot in one change. So what that does is actually reduces our possible subspace to uh, well, if we try all possible combinations, we'll only have to check those combinations that um, that are one distance apart. So to store it, we can simply store it in a map. And so against a word, we will store all those words which are one distance apart. And then what we can do is iterate on our list, and that list is going to contain the first element, but not the last one, and our dictionary. And what we'll be doing is starting from the first one, we look for it in our map, and whatever the value is, for those values again we will look in our map. Now we need to take care of some things, like we don't need to be coming back to our old search. So basically you don't want to go from hit to hot to hit. So maybe you can just remove it from the map while passing it down. So it'll not remove from the map permanently, but only for that search, that sequence. And in that case, if uh, if you do find a key in the map, means if you do find the any value against that key in the map, means you can possibly convert this to something else, or else you can't. And we'll while looping, we'll uh, through the values in the maps, we will check that if the value matches our end word, so we've found our answer, right? And so that'll be our sequence. So we can keep track of that sequence and just push that sequence in our result. That seems like one possible answer to me. So what we'll be having is one helper function that will be iterating through that has checks regarding uh, the map. Regarding whether the key is found in the map or not. Then we have to exit whether the uh, and then it has to iterate through our input for the input key in the map, and all the values that are against that key we have to check if, let me write that down. So our helper function, that's what we call our recursive function generally. So we'll be passing the last key that we found, and for each value in map key, we will be checking if value is the end word, the end word. It's the end word, then return path, and if it's not, then we call the helper function with value as a new key. And if the map key is empty, then we just return because it means we didn't find anything. We can't convert this to our result essentially. And before this, we also remove a value from map. So we don't remove it as a key, but instead we remove everywhere it occurs as a value. So the complexity of finding is pretty high, I think. And before all this, what you have to do is create that map by comparing all the elements in our array. Hmm. So see, hot will have dog, dot will have dog, dog will not have anything. Sorry, dog will have log, and log can be converted to cog. Oh, okay. So since this word is already in our end list, so we don't have to add it. So we just have to check if this, I mean, whatever value we have is, yeah, we don't have to add it while creating the map, essentially. Yeah, this is another thing. Um, hmm. In fact, now that you look at it, um, instead of doing our helper function in this order, that is going from the start to the end, we'll actually go in the opposite direction. That is, see what map cog is, and for its values, we run the helper, and uh, in that way, if we're able to reach HIT, means there is a solution. This would be better. I mean, of course, both methods are correct, this and the other one, but this would be better um, if there is, a single path, maybe single, like the lesser the options. But for going from hit to other options, so say hit can be converted into um, two words, hot and maybe him. And then they can themselves be converted to two. So you'll be checking this set and this set and all the possible, sets they're all creating. Uh, and maybe just this one is the answer. So this will come up much later. But say if this can be only made from this one, and if this can be only made from him, and then can be only made from hit. So you straight up have your answer. Okay, I think that should be the solution. For calculating the distance, it's fairly simple, I think. So, of course, it has to be n square, where n is the length of your uh, word, since you have to calculate the distance between each word. So, for I 0 to n, and for j 0 to n, uh, if I not equal to j, so you need to do it. So actually we can do this, just do I plus 1. I was doubtful about it because we needed to create the map from A to B and from B to A as well, but I think we can do it here itself, where we check that if distance between uh, your word list I and word list j is equal to 1, then map list I is equal dot insert uh, list j, and map list j dot insert list I. Yeah. Yep. This will make our map, and this distance function would basically be string 1 and string 2 for I equal to 0 to length of string 1 or 2. Um, you keep a counter if s1 I is not equal to s2 I, count plus plus, and if count, you can stop here or add this condition in between as well. If count is greater than 1, return count, or when the loop ends, then you can just return 1. Since the words won't be same, none of the words are same, so you'll never return 0 anyway. Yeah, so this is our distance function. So this will run for a length of the word. Let's say the length of the word is k. Now this is going to run n square times, and this is just creating the map. So this is going to be different from finding our answer. Now finding the answer, that totally depends on the size of the map. So it's actually, honestly, it could be anything. But say one of the words maps to two, so the final set is reduced by two. So you only have those many options. So so it'll actually be sort of order of P, where mm, there's no fixed number that I can give you for this. Maybe because I'm not very sure of what it'll be. Okay, so this is my solution. Uh, let's see in the discussions maybe once if there's a better solution or something. BFS. super fast. 2 and BFS. Ah, 2 and BFS. That's a good one. Um, huh. When we solved it in the key ideas doing BFS of paths instead of words, then the queue becomes a queue of paths. Okay, unordered set visited level 1 while paths are not empty. Path.front, path.pop, while path.size greater than 1. For each word in visited, wordlist.erase the word. Clear visited. If path size is greater than minimum level break, I'm saying it went on indefinitely or something, which is not even possible. Else level equals path dot size. Last is path dot back. Right now path has nothing. For each character in A to Z, next word is in the word list. Expect this. Hmm. I don't really like this. I don't really like this solution. This looks very brute force. Brute forcey. Using a map to store the minimum ladder of each word. Use a set to store the words visited in the current ladder. When the visited ladder was completed, delete the visited words from the unvisited. That's why I have two similar solutions. Do not compare if their difference is 1. If is to construct a graph, if is to construct path from end to start with. Okay. One word is allowed to be inserted in the queue only once. So they made a graph. Let's just see this get neighbors. So why is this different? What they're doing is for the length of the string, they check if the oh, they're adding like every possible word that it can be converted to as neighbor, which is unnecessary space, I would believe. And they're just checking in here like if the neighbor uh mm, uh, what is your answer, mate? You didn't update the results in the BFS. Hmm. Okay, this is also a solution. Why should I deny it? And DFS says for each neighbor, if distance of the neighbor equal to distance plus 1, just in this is just in case the next node is the next level of the current node, otherwise it or the parent or it is not the shortest node. And how are you calculating distance again? Hmm, not sure. This is more optimal than what we talked about. So he made two maps, and then I guess he was talking about generating um hmm, yeah, so this is I think what I was talking about is to check if we can reach not sure if we can reach our destination from our source in steps. Okay, I'm not um I mean if you actually want me to code the answer to make sure that it our logic does work. The root node can yield all the children node, and the second layer of the tree, second layer can yield all the children, third and so on. The one tree yields a new child. We search it in the last layer of the other tree. If we find an identical node in that tree, we get some ladder to connect. Another thing that should be considered, two different. So I don't think we really need to make a change in the data structure or anything. Can handle using existing data structures using maps very easily. So yeah, I think this guy is actually using my logic finally, and it does say the fastest C++ solution. So yeah, like I said, I'm pretty sure this one is much better than the other ones. Cool. So I'm not gonna spend so much time in actually writing that solution down over here. I will do it later on for sure, and I'll show you guys the solution. For now, you can just believe me that that solution will actually work. Okay, awesome. Word ladder, medium, nice. Given two words and a dictionary word, find the length the shortest transformation sequence from begin to end, such that only one letter can be changed the time. Hmm. It's the same thing, but this is medium. I guess the solution for this would remain the same, except that. Hmm. So I think you can do BFS with a visited node. Um, so keep a map for visited, and from each node, uh, again you need the distance thing. If the distance is 1, then uh, you can mark them as the children of that node. Or again, we keep a map from that node to our to the one distant words, and if you've already visited that, then we don't visit it, and if you not visited before, we add one to the count and call our add it to the queue actually, and keep going till we find the word. And as soon as you find the word, that is our answer. Because in BFS, as soon as you find your target, you get your minimum answer, so to say. Cool. And if your queue ends without finding the word, then your answer is zero, essentially. Yeah. Awesome. So I'm not expecting anything else to be discussed here. Simple BFS and just checking if the distance is 1 between this word and any of the words. And I'm hoping there is. So they're erasing it from the dictionary. You can keep a visited array as well, visited map as well. Okay, I think we're coming up to sort of design questions more, and yeah, more of system design and sort of game design or any design. So I don't think I will be able to answer those questions because I have not required to solve. Okay, we'll study that later. Yeah, because I have not, I don't have a good grip on system design as of yet. So I would suggest that I study those first and then I introduce you guys to those questions. At least I feel I should have some past experience. Like all these questions that I've done with you, I do have some past experience, at least in these topics, to yeah, to sort of help you out with these questions. So 23711. Longest increasing subsequence. This is a very typical question. Um, so let me show you visually what this question is actually all about. So it's asking for the longest increasing subsequence, right? So say you have this example here, cell 10, 9, 2, 5, 3. My 2, 5, 3 is a little long. 2, 5, 3, 7, 101, and 18. So if you can see here, this is our longest increasing subsequence. These four elements, 1, 2, 3, and 4. Hmm. So this is a stack question. Uh, it is really hard to come up with the solution without having either a very good grip on stacks. You've done a lot of stacks question without actually knowing what this sort of algorithm is, um, or without actually having done this question before. It's really hard to figure it out. So let me see if I can actually intuitively make you understand this, uh, make you understand this algo without making you feel like that you couldn't do it without knowing the actual logic. So basically trying to explain what's happening and why we're getting the result that we're getting. So let's just do it intuitively and see what happens as we iterate in our array. So it's saying, could you improve it to O n log n, and it should run in O n square. So I'm not even aware of the n square solution, I think. Uh, okay, so let me show you what I'm talking about. So let's say you start with the first element here, and the next one decreases. So say there are some elements that are going to be greater than 10 that come after 9. This was 10, this was 9. So if we consider 10 as our as part of the answer, then this will be our result and the result would be 5. But if we consider 9 as an answer, it would also be 5. But say there were elements between 9 and 10, 10 would have ignored those in our result, but 9 would not have. Now you might be considering, okay, this case is only for the first two elements, might be different for other examples, but we'll see why that's not so. Say if there were some elements that were before 10, that were between 9 and 10, and they were included in our answer, and they would have also included these, and then, something better would have happened. So you'll know why what we'll be doing now is definitely going to be the best result, going to give the best result. So basically, when you see a decreasing sequence, you don't want all the numbers before your current element that make your sequence a decreasing one. So basically, when we start, we put 10 in our sequence. Sorry. When we start, we put 10 in our sequence. Just follow the actual sequence from the example. So we put 10 in our sequence. Then when we encounter 9, we see, okay, all the elements that are uh, greater than 9 need to be removed straight up. So we remove 10 and now we have 9. Then we encounter 2, and we remove all elements that we encounter that are less than 2. Then we encounter 5, so we add 5 since this is still increasing. Then we encounter 3. Now since 3 is less than our set here, we remove all elements that are greater than 3. So now our set becomes 2, 3. Then we get 7, we get 101, and we get 18. So 101 had this length 4. Whether or not you include 18 in that doesn't matter. So for the last element, if our logic stands still, we get 18 instead of 101, and then our sequence becomes of length 4. Say we had another number after 18. If this would have been our longest sequence and we would have not removed this huge number and replaced it with 18, we wouldn't have been able to accommodate 20, but now we will be, so it becomes 5 in that case. So this happens essentially, what happens is, let's take a case to disprove this logic, yeah? So say we had included this here and had not removed 5 when we encountered 2, and we were saying that the elements that were before 5 could have been such that would have given us a better result. So yeah, for the short term, we could have had tons of elements here greater than 2 between 1 and 5 that would have given us a good number. So whatever the size of that array was at that time of our result, we would have stored that as the possible maximum if it was the current maximum. But going forward, uh, we'll be missing on all the elements over here if we include this. So you don't. So you don't include this element. Now, what about an example like, so you're saying this is 1, this is 5, and there are 100 elements between this, and then we get a 2, and we have a 16. So our greatest sequence would be 1, those 100 elements, the 5, and then 16. But instead, if we follow this logic, it would be 1, then those 100 elements, then we get the 5, then 2 replaces most of those. Say we have only 50 elements left, or 2, and then 16. So how is that better than this? Good question. Find the length of the longest increasing subsequence. Hmm. Now I have doubts on my own knowledge. So let me just look at the answer with you guys quickly. For all numbers, the iterator is, what is lower bound? Which does not compare less than value. Oh, so the first number greater than nums. If it's not the end, then you add that to your result. Else, if you didn't find that number, if you didn't find a number which is greater than nums, then we add that to our value. Else, hmm, lower bound at position 3. 0, 1, 2, 3. What is the value? 20. The first item in the list which does not compare less than value, which is greater than the value, you mean. So it's 3, 0, 1, 2. It might not be 0, it might be 1, 2, 3. So this first number greater than this. So find the first number greater than I. If it exists, if it does not exist, okay, I'm not sure what that solution is then. Let's try and see another one. 6, 7, pre-process. comes 1 2 7. Sorry, I don't think you got the question, dude. I have no idea what's happening here. Think I'm gonna have to study, I mean, read the post. Oh, that was the O(n) square solution, I think. For n, it goes n times. For n, it will go n times. So yeah, that is O(n). Let me see. What will be the answer? Let's check our case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 16. So the answer should be 11. If it gives 10, then I'm doubtful about the logic that I thought. And yeah, okay, so this is giving 11. Hmm. Oh, n square. Not sure it needs dp, but oh, hmm. Then what is that problem a solution to? That the algorithm I just told you guys about is also a solution to some problem. Why would I make up something? Um, so this is basically for each I, you check the all the increasing j's before it. So if a number is greater than that your answer, sorry, if select a target, and if all the index, if an index before that target is less than your target, then update your, what is t, if the length of the number of numbers less than I is at that target, increase it by 1. Hmm. Who's this great guy? Is he? Yeah. Is this guy, man. This guy is a lot of Hmm. I need a ON square without. I need to find what is the logic that I am talking about. Hmm. Okay, I'll see what that is soon enough. Okay, so for now we actually did get stuck in these questions. This was probably medium, I think. Oh, it does have a solution. Okay, recursion with memoization. Scan the array from left to right. We also make use of DP array initialized with all zeros. The DP array is meant to store the increasing subsequence formed by including the currently encountered element. While traversing the array, we keep on filling DP array with the elements encountered so far. For elements corresponding to the jth index, we determine its correct position in the DP array, say ith index, by making use of binary search, which can be used since the DP array is storing increasing subsequence and also insert it at the correct position. An important point to be noted is that binary search we only consider only the portion of the DPR in which we have made the updates by inserting some elements at the correct position, which remain always sorted. Thus, only the elements up to the ith index of the DP array can be, yeah, okay. Since the elements entered in the correct position in an ascending order in the DP array, the sequence formed in so far in it is surely an increasing subsequence. Whenever this position index becomes equal to the length of the means we need to update the length as length plus 1. dp does not result in longest increasing, but the length of the dp will give you the length of the ls, which is not the longest sequence, but the length. Okay, so we have 0, we have 8, now we have 4, we have 12. Why? Um, why? Probably this guy explains why. Yeah, this is the DP solution. Hmm. What about this one? So freaky. Hmm. Okay, just for making sure that solution is not nearest smaller element. I think it's this actually. Hmm. Nearest smallest element for every AI in the array such that the element has an index smaller than I. Nearest smallest element. So, hmm. Well, I've done questions with this thing before. I did an interview question as well, but I'm not able to remember what the question was now. I've done some stacks questions as well. Hmm. Anyway, okay. So that was a weird one. So I yeah, that's why the solution that I was giving failed for one condition, uh, because there was the wrong solution. So, with that, I think we'll end the stream right now. And um, if you're able to do these questions with me, well and good. If not, go ahead and practice them again. Um, I'm not an expert in understanding what's the best way for you to learn. It's for you to decide. For me, what helped was just practice. That's all. Yeah, if you really enjoy it, then I think you like it better. So try and enjoy it. Don't look at it as work.